So we have a phonograph turntable rotating at 33.333 RPM, right? Revolutions per minute. A small object is on the turntable 6 centimeters. Now centimeters you got to watch, right? Because it's not a meter here. From the axis of rotation. A, calculate the acceleration of the object as assuming that it does not slip. And B, what is the minimum value of the coefficient of static friction between the object and the turntable? And suppose that turntable achieves the angular speed by starting from rest and undergoes a constant angular acceleration of 0.25 seconds. Calculate the minimum coefficient of static friction required for object not to slip during the accelerated period. Okay, so let's take a look. For part A, calculate the acceleration of the object as assuming that it does not slip. Now we know this right here is omega, right? And this omega is equal to 33 1/3 revolutions per minute, right? So we need to convert this into radians per second. So in 1 revolution, there are 2 pi radians, right? And then, obviously, in 1 minute, there are 60 seconds, right? So hopefully, we should be able to convert that into 3.49 radians per second as my omega, all right? And that's good to know. So if we have to think about V is equal to omega r, right? Therefore, since we have 3.49 radians per second times r, which is 0.06 meters, we should keep everything in meters, kilograms, and seconds. This should come out to 0.2094 meters per second. Okay? So, well, if it's turning at a constant rate as this, you're not going to have a tangential acceleration, right? Because it's really not speeding up or slowing down. Therefore, A tangential is equal to 0, right? However, because it's turning, right, we're definitely going to have a rotational, right, which is v squared divided by r. Therefore, since we got the v here, so 0.2094 divided by the radius r, let's square that by the way, 0.06, I believe we get something like 0.73 meters per second squared, right? So for total acceleration, we only have radial acceleration, okay? And this is, right, towards the center of the circle, right? Okay? So A total, right, which is basically, I guess square root of A tangential squared plus A radial squared. So you're just going to get this, which is 0.73 meters per second squared. All right. So let's take a look at part B. Now we're looking at this from side view, which means like we're looking at it like at the record level, at the turntable level. We're looking at it like this, right? So our eyeballs like right here, right, at the same height as the turntable, and this is what we will see. Okay. So if we were to take a look at, so what is the minimum value coefficient? So what's keeping this coin or this object on the turntable is basically friction, right? Friction is keeping this thing on the turntable, and friction is pulling this towards the center to keep the object in a circular motion, right? So friction is keeping this thing in a circular motion. So friction is that, and we have Fg and F normal, right? And obviously F normal and Fg are same values because there are no other forces vertically. And you know friction is equal to mu times F normal, right? So now we have pretty much all the ingredients we need to work this thing out, right? So since friction, which color should I use? I'll use red. All right, sum of all forces in the x direction is equal to MAC, right? Because it's going in a centripetal acceleration here. Right? Then sum of all forces in the x direction, there's only one, and that's F friction. Since AC and friction are in the same direction, we're going to keep both of them positive because we always want to make the AC positive direction because you don't want to confuse ourselves, right? So make AC positive direction, okay? Therefore, F friction is also positive, right? So we could say MAC is equal to F friction. So mv squared over r is equal to mu times, we know the normal force is mg, so I'm going to just do that. So we didn't even have to know the mass of the object, because object's mass will cancel out, and we can solve for mu, right? So our mu is equal to v squared over rg, right? Therefore, 0.2094 squared over 0.06 times 9.8. So our mu should come out to 0.075. I don't know, check the math on that. So, all right. Any questions? All right, so what about part C? Now suppose that the turntable achieving its angular speed by starting from rest. So now we are looking at this part when we're first starting out, right? So it starts from rest and undergoes constant angular acceleration for 0.25 seconds. Calculate the minimum static coefficient of friction required to keep the object from not slipping. All right. So, all right. If we start out, so we're going to say force total is equal to, right, F tangential plus F radial. Now, when I say that, because it starts from rest, not only does it have to start this thing by keeping it on the turntable tangentially, as well as keeping keeping it radially to keep it going in a circular motion. So we're going to have two different forces acting on this. So force radial which is the frictional force, and then force tangential, which is also a frictional force. There are two frictions happening simultaneously. Okay? So total force is basically mu times F normal, which is the frictional force, the total friction, right? And that is equal to MA tangential plus MA radial. Okay? And of course, this is tangential hat and this is radial hat, right? If you want to keep that in there to make it more legit, right? So let's figure out what's going on, okay? Radial, I think we already got it. We already know, what the A radial is, right? It's V squared over R, right? Here, tangentially, we have to figure that out. So we know omega final is equal to omega initial plus alpha t, right? Let's calculate how much angular acceleration it goes through, okay? So we know it's traveling at 3.49 radians per second. So it has to achieve this from rest at 0.25 seconds. Does that make sense? Right? So here, 3.49 radians per second is equal to, initially we start at rest, so this is 0, plus alpha times 0.25 seconds. So what's my alpha? So my alpha is equal to, if you divide this by 0.25, I get something like 13.96 radians per second squared. So A tangential is equal to alpha r. So my A tangential is equal to 13.96 times 0.06 meters. So my A tangential comes out to 0.84 meters per second squared. So once we know that, we have this. So now we can calculate mu times mg is equal to m times 0.84 times, well, plus m times, this is tangential head, by the way, sorry. I always forget that. M times A radial. So what's A radial? A radial is A sub c, which is equal to V squared over R, right? And V squared, which is 0.2 whatever, right? Which is right here, which is 0.73 meters per second, right? Radial direction. So they're perpendicular to one another, okay? So here, masses can cancel out nicely, okay? So mu times 9.8 is equal to, right, basically this, okay? So here you got 0.84 tangential hat plus 0.73 radial hat. So the magnitude of this is really nothing more than square root of 0.84 squared plus 0.73 squared, right? Which is equal to 1.113, which is mu times 9.8. So mu comes out to 0.11. All right. All right. Can we move on? I'll post these so you don't have to. All right, now let's take a look at some good stuff. So we're going to actually calculate the rotational inertia of a meter stick with mass of 0.56 kilograms about the axis perpendicular to the stick located at 20 center mark. So instead of rotating it right at 50 meter mark, which will be nice and balanced, we're going to rotate it at 20 center mark, and that's going to like wobble around crazy, right? So we're going to have to use the parallel axis theorem. So this is right here, this is the H. H is how much, um, you know, the axis is away from the center of mass axis, right? And of course, we know the moment of inertia parallel axis is equal to I sub Cm plus mh squared, right? The I sub Cm for a rod rotated at the center happens to be 1/12 ml squared, right? That's on the last page of your notes. Plus mh squared, okay? So 1/12 times the mass happens to be 0.56. The length happens to be 1 meter because it's a meter stick. And some students were asking, well, what's the length of it? I don't get it. Well, it's a meter stick, so it's a 1 meter, duh, right? Plus 0.56 times h, which happens to be 30 centimeters, or simply 0.3 meters squared. And rest is all math, so no magic involved. So if you add them up, that is the moment of inertia for this system. All right. So now, isn't it great? Yeah. They're all seated by their arranged seats. Like they're seated by the, like permanently like assigned seats. Yeah. I know. Right. Yeah, I usually give freedom to my students. I treat you like adults, but unfortunately, pandemic's not making me do that. All right. Let's take a look at the next problem. So here we have a torque happening, right? Now we have to recognize what the force is, what the radius is before we actually start doing the torque itself, right? Now we know torque, just by definition, simply torque is equal to R cross F, right? So here, if I were to, this is the pivot point right here, right? This is the pivot point. So if I were to redraw this from the common pivot point, here's my R, right? Again, it's a common pivot point. And here's my F. See this? I'm going to slide it up there. So here's my F, like so. The force happens to be just the weight of this bob, I guess, right? This here is massless, luckily, because if this has mass, then we would have to think about having a moment of inertia for this rod as well as moment of inertia for this mass. But this is actually massless rod, which makes it a lot easier. Okay, so we just have to worry about just the weight of this, I guess, bob, a ball, right? So here, my torque is equal to then R cross F. What's my R? 1.25, right? 1.25. And this angle, of course, here is 30 degrees. So 1.25 times force of this is 0.75 times 9.8. That's the force, right? Therefore, times sine of 30 degrees, now comes the direction part. Which way is the direction of my torque? How do we find direction of torque? Come on. We have to use what? Thank you. Louder. The right-hand rule. So you have to use R cross F. So R cross F, and my thumb points into the page, so it's negative Z hat, right? Don't try to break your wrist, but you could rotate your, page around, and then do R cross F, and then you'll see the thumb is pointing into the page. Therefore, it is negative Z hat. Okay? So my torque comes out to, it should come out to 4.6 meter newtons, negative Z hat. Okay? That means it's going to be turning clockwise. All right? Clockwise direction. All right. Any questions? Are we okay? All right. Good. Next. When a torque of 32 Newton meters or meter newtons is applied to a certain wheel, right, it acquires an angular acceleration of this many radians per second squared. So my angular acceleration alpha is 25.0 radians per second squared. When a torque, tau, happens to be 32.0, I like meter newtons, just to keep it separate from Newton meters, which is work, but torque, I'm going to keep it meter newtons. I'm old school, I'm sorry. What is the rotational inertia of the wheel? Rotational inertia is just basically moment of inertia. They're looking for the moment of inertia. Okay, so since torque is equal to I alpha, this is so hard. 32.0 is equal to I times 25.0. Oh my goodness, how do I do this? Ah, the difficulty. All right, that was really hard. And look how much room there was left over here. just to freak you guys out. It's like, oh my God, I only took you like 2 steps. Maybe I'm doing something wrong. I'm supposed to fill this whole page. Nah, no, sometimes it's just easy. All right, it's just I alpha. Torque is equal to I alpha. All right, let's take a look at 74. We have this system going on here. This is the pivot point. This is very important, right? This is the pivot point, right? So in this figure, 2 blocks, each with mass m, suspended from the end of a rigid weightless rod. So that's good to know. So we have one less thing to worry about. If this rod actually had mass, then we have to use parallel axis theorem for the moment of inertia of the rod and all the other good stuff. But we don't have to worry about that. The length of L1 plus L2, so this plus this, with L1 being 20 centimeters and L2 being 80 centimeters. This is like a meter stick, basically. The rod is held in a horizontal position as shown in the figure, then released. Calculate the accelerations, look at this, accelerations of the 2 blocks as they start to move. Okay? So what are the accelerations? So there's going to be 2 accelerations happening, right? So when they're asking for accelerations, I'm thinking like a tangential acceleration, okay? So what we need to do is we need to find, right, the torque, right? We need to find the torque, which will cause angular acceleration. Once we get angular acceleration, then we can figure out the tangential acceleration by multiplying by its appropriate radii, right? So I always like to start out with like Newton's second law. Sum of all torques is equal to I total alpha. I just like to start with that. Just like the way I always start with F equals ma, I like to start with torque is equal to I alpha. Okay? Now, since alpha is same for both of these, because they're going to rotate at the same rate, even though their locations are going to be different in meters as far as the radius is concerned. So the rotational alpha or angular acceleration will be the same for both of these, right? So this is a common alpha for both masses. Then my second sum of all torque is equal to torque 1 plus torque 2. Torque 1 is caused by mass 1. Torque 2 is caused by mass 2. Right? So let's calculate torque 1 here. Torque 1 is equal to then, right? Here, it looks like the pivot point is here. Here's my R1, which is L1. Here's my F1, which is M1G. The angle between it is 90 degrees, so theta is 90. So torque 1 is equal to R1 times F1 times sine of theta 1, right? Now, what is the direction? R cross F. Come on. Positive Z, correct. So my R1 is L1, which is 0.20, times F1, which is just mg, times sine of 90 positive z hat. Right? Therefore, this is 1. Right? This is 1. So I get 0.2 mg positive z hat. What about my torque 2? My torque 2 is equal to R2 F2 times sine of theta 2 n hat. Well, my torque 2 is, here's my pivot point. Here is my R2, which is L2. Here's my F2, which is M2G. So R2, 0.8 meters times F2, which is still mg, times sine of 90 degrees. And the direction of this is R2, F2. Come on. Negative z hat. Good. Right? Negative z hat. So this would be negative 0.8 mg z hat. So let's add them up. So I'm going to set them equal to each other. I total alpha is equal to, right, torque 1 plus minus torque 2. So I, which is, we should do the I total is equal to I1 plus I2. I1 is mr1 square, m1r1 square, because we're going to treat these as like particles. And then I2 is m2r2 squared. Therefore, m1 is just m times 0.2 squared plus m2 is just still m times 0.8 squared. So what's my I total? Well, what's 0.2 squared? Like 0.04, right? M plus this is 0.64, right? M. So it is 0.68 M is my I total. So now I have all the ingredients to calculate for my alpha. All right, so here we can say I total is equal to 0.68 M times alpha is equal to torque 1 is 0.2 mg minus 0.8 mg z hat. Right? So look what happens to my mass. My masses all cancel out nicely. Right? Giving me, what does it give me? Well, here, I guess 0.6 times 9.8 is, what's that? 0.6 times 9.8, negative 0.6, negative, I get 5.88, right? And then here, I get 0.68 alpha. So my alpha comes out to negative 8.647 radians per second squared z hat. So that's my alpha. Therefore, for M1, right, my A tangential is equal to alpha R, 1. Right? So A tangential for mass 1 is equal to alpha, which is, we're just going to use, we know which way alpha is. I just want to find the magnitude of my A tangential first. We could always give directions to that after we find the magnitude. So I'm going to just use 8.647 for now, okay, times R1, which is 0.2 meters. So my A tangential, just the magnitude wise, okay, happens to be 1.73 meters per second squared. Okay, so that's how fast this acceleration is for my M1. And for my M2, A tangential 2 is equal to alpha R2, and that is equal to, again, 8.647 times 0.8. So this comes out to 6.92 meters per second squared for my A tangential 2. Okay. So I think it's important to start with torque is equal to I alpha. Right? Once you start with torque is equal to I alpha, then you set that equal to torque 1 plus torque 2 plus torque 3, etc., etc. Then set those two equal to each other. Then you have to find each ingredient, like either I, alpha, torque 1, torque 2, torque 3. Find those individual variables, right? So once you start with this, then you identify the torques, then you set them equal to each other, then you find all the ingredients for this. And torque 1, we said it was R1 cross F1, right? Torque 2, R2 cross F2, torque, 3, whatever, right? Then you find the moment of inertia for the total system, moment of inertia for mass 1 and mass 2, then total moment of inertia. Then you plug it back into this I alpha is equal to torque 1 minus torque 2. Then it's just algebra from there, really, right? Now, once you know your alpha, this negative only tells you that it's going to turn clockwise, really. That's all it really tells you, right? This alpha being negative tells you that it's turning clockwise. Now, once you know it's turning clockwise, you just have to figure out the acceleration, tangential acceleration, because this is going to accelerate that way, and this is going to accelerate this way. So, there's no like negative involved. If you put negative in there, that means it's going to slow down, but it's not slowing down. It's actually speeding up. Okay, so we're not going to put negative in there. Right? So this negative, right? That's all that negative is telling you. Okay, it doesn't mean it's slowing down. All right, any other questions? All right, want to keep going, or you want to take a break? You guys are true AP students. You don't answer. Then we'll just keep going. All right. All right, here we go. This looks like fun. Two identical blocks, each of mass m, are connected by a string over a pulley with radius r and the moment of inertia I, right? So this pulley now is no longer frictionless or massless. This will resist from rotating because it has mass. That means the tension for this rope are not going to be the same because there's going to be resistance right here. So you cannot set these two tensions equal to each other in this case. String does not slip on the pulley. It is not known whether or not there is friction between the table and the sliding block. So we don't even know if there's a friction there. When this system is released, it is found the pulley turns through angle of theta in time t. Holy shnikes. We have no numbers, right? So this is basically position, angular position as a function of time. That means we better use one of those, like, hopefully constant acceleration equations. The acceleration of the block is constant. That means now, yes, we could definitely use the constant acceleration equation. So this theta is equal to theta naught plus omega I t plus 1/2 alpha t squared is probably something we can use. A, what is the angular acceleration of the pulley? So they want to know what alpha is. B, what is the acceleration of the two blocks? They're probably talking about tangential acceleration, right? Or linear acceleration. C, what are the tensions in the upper and lower section of the string? All answers are to be expressed in terms of M, I, R, theta, G, and T. Believe it or not, this is how they ask at college right now. And it's all in multiple choice thing too sometimes. And you have to like plug it in into this computer. So there's no partial credit at college, especially when they're doing it online. So get used to these kind of problems when you go to college next year, or for some of you in 2 years. One of my sons is studying physics at Michigan, and they're doing it like this. It's crazy. All right, so let's take a look. So for part A, they're looking for what is the angular acceleration of the pulley. Now we know since it is moving at a constant velocity, we could probably say theta of t is equal to theta naught plus omega initial t plus 1/2 alpha t squared, right? So, I mean, I don't know if we could assume that this is going to be starting at 0 location, right? So, I mean, if we do say if it starts at 0 location, I mean, I wouldn't say why not, right? I mean, it probably, wherever it starts, we're going to call it 0, right? And it also starts from rest, right? Because we hold on to this and then we release it. So now it's going to start to move. So we know that this is 0 and this is 0. So theta, which is basically, is equal to 1/2 alpha t squared. So whatever the theta that we get at this time t, right, is what we have. So alpha is equal to 2 theta, right, over t squared. I mean, if you feel like if this is not 0, then alternative way would be you say delta theta is equal to omega initial t plus 1/2 alpha t squared. Then this becomes just delta theta, right? So it's not that much difference. Yeah, why don't we do that then? If you want to do that, so we do that delta theta. All right. What about B? What about B? For part B, what is the acceleration of the two blocks? Well, if this thing is going to be rotating without the rope slipping, right, this tangential acceleration of the rope has to be same for both blocks. Okay? So, sorry, this is A, this is B. So if we could say that alpha of that pulley can determine how fast the rope is also accelerating, which means how fast the blocks are accelerating too, right? So A tangential for the pulley can determine by alpha R. So we can say 2 delta theta R over T squared, right, is pretty much A tangential. All right? Then, now if we were to put this in the computer answer key thing, they'll probably mark it wrong because they probably want it in terms of theta. It's very frustrating, so be careful. That's why I don't actually use that. We have that program here too, but we don't use it because I think students find it a lot frustrating using that. C, let's figure out what are the tensions of each one, right? Well, if we were to think about it, for tension 2 is the easy one, right? Because tension 2, and we don't know if there's friction or not, so we're not going to assume there's friction right now. If there is friction, I guess then we can work it out. But sum of all forces for, block 2 is equal to, right? And block 2 is also M, right? MA. And there's only one force. That's tension 2. So tension 2 is equal to MA, right? A tangential. So tension 2 is equal to, right? Um, mm-hmm. Yeah, it's going to get a little bit more involved, I guess. And we'll leave it at that for now. Okay, we'll leave it at that. Then, if we take a look at M1, right? Here, I have M1G and I have T1, right? So it looks like sum of all force 1 is equal to M1A, right? And sum of all force 1 is equal to, it looks like this is going to be positive direction, right? So mg minus T1, right? So here, if we set them up, then tension 1 is equal to mg minus ma, right? So tension 1 is equal to, I guess we could put this A in here, m times g minus, right, 2 delta theta r over T squared as my tension 1. Now for my tension 2. Okay. Tension 2, there's going to be torque involved right here. Right? I mean, this is the obvious answer for tension 2, really. But it can't be that simple. So if we were to look at this, there's T1, and then there's T2, right? And there's torque causing this by R and R, okay? So sum of all torque is equal to I alpha. Sum of all torque is equal to, now T1, if you were to think about T1, torque 1 is equal to R cross T1, right? What's the direction of that? R cross T1. Right? R cross T1, it has to be negative Z hat. Yeah? So that's negative torque 1. And R cross T2 is positive. So again, torque 1 is just basically R times T1, right? Times sine of 90. We already determined the answer for that to be negative Z hat for the direction. So this is R T1 negative Z hat. And then for torque 2, same thing, but it's just positive Z hat. Right? So I alpha is equal to negative RT1 plus RT2. Well, what's my moment of inertia? Moment of inertia for disk is 1/2 m. Oh, I guess they just wanted an I. So I alpha is equal to, right? We already figured out the T1 part, right? So R negative R times this T1 can be plugged into here, right? So it would be M times G minus 2 delta theta R over T squared plus RT2. All right. Now what? I guess we could sort of distribute all these out, right? It's just an algebraic mess, really, right? So if we divide both sides by R, we got I alpha R, right, is equal to mg negative, I guess, negative mg plus m2 delta theta R over T squared plus T2. So if I bring all this to the other side, my T2 basically becomes I alpha over R plus mg minus all this mess right here, right? M times 2 delta theta R over t squared. And since they don't want this alpha, you have to replace that with 2 delta theta. So T2 is equal to 2 times I delta theta over T squared plus mg minus 2 m delta theta r over T squared. Holy shnikes. Yeah, that's it. I mean, I guess this is really not wrong, but they want it in terms of I's, you know. So I guess this is the most trivial answer, but this is what they really want. All right. All right, one more. Well, actually, no, not just one more. Let's keep moving. Here we have if 12 centimeters, R is equal to 12 centimeters. Don't forget that's centimeters. M is equal to 400 grams. So that's important. Small hanging mass is 50 grams. All right. So we should really use that MKS system, meters, kilograms, seconds. Right. So in the figure to the right, find the speed of M after it has descended 50 centimeters, starting from rest. Okay. We should definitely use energy consideration in this. Since they didn't say anything about friction here, right? Solve the problem using energy conservation principle, right? Repeat with 5 centimeters instead of 12 centimeters. Wow. So since work done by friction is equal to 0, therefore we're going to say total energy initial is equal to total energy final. Okay? We're going to assume that. And total energy initial is just simply potential energy of this hanging mass. Okay? So potential energy of small m. That's the only initial energy we start with. And it will have height of half a meter. Okay? However, total energy final is when this thing is actually, spinning, and then this thing actually is down here moving. So this has kinetic energy, right? This also has kinetic energy rotational, right? So this potential energy has to turn into these two kinetic energies. Okay? So I have kinetic energy rotational for the disk plus, I'm assuming that it's a disk, right? Plus kinetic energy of this hanging mass. So here I have mg y initial is equal to 1/2 I omega squared, right, plus 1/2 this m, right, this m, v final squared. However, this omega of this thing rotating, right, this omega is equal to v over r, because this tangential velocity is same as this string or this block velocity is the same thing. speed of this block and the tangential velocity of this disk, it has to be the same. Okay? Therefore, if we substitute that in here, I have mgy initial is equal to 1/2 mr squared. This m is this disk's m times vf squared over r squared, because you have to square the omega, plus 1/2 mvf squared. Now this vf and this vf are the same vfs because they're attached to one another. Okay? Now, notice how this r squared and this r squared can get canceled out. Okay? Don't cancel out the m's because they're not the same m's. Okay? So let's plug in some values. Here, this small mass is 0.050 times 9.8 times 0.5 is equal to, here I have 1/4 times 0.4 kilograms times VF squared plus 1/2 times 0.05, right, times VF squared. Well, you know now, rest is algebra, right? So here I get 0.25, something like that, or 0.245 is equal to, what is this mess right here? This looks like 0.1 VF squared, and this plus, this looks like 0.025, right? VF squared. So add them up, divide both sides by 0.125. So my VF, and then take square root, right, is equal to square root of, I guess, 0.245 over 0.125. So you should get something like 1.4 meters per second. Now, that was part A. Now let's do part B. Repeat it with 5 centimeters. Well, what's the only thing that's going to be different? This looks like instead of 12 centimeters here, this is going to just turn into 5 centimeters. So does that make a difference? No. It's the same thing, right? Right? Since r squared is gone, same thing. All right? All right. Let's take a look at 18. I'll help you set this up. Okay. So here, uniform spherical shell. So you have to look for the moment of inertia for the shell, I guess, right? With mass m and r, right, rotates at a vertical axis of frictionless bearings. A massless cord passes around the equator of the shell over a pulley of rotational inertia I, which is 1/2 mr squared, but I guess they just want you to use I for the disk, right? Just I. And the radius r, and is attached to a small object of mass m again. that is otherwise free to fall under influence of gravity. There's no friction on the pulley's axle, so there's no friction here. Right? That means if there's no friction, then we can use total energy initial is equal to total energy final. Right? The core does not slip on the pulley. That means the VF here is equal to VF here as well as VF tangential here, right? And what is the speed of the object after it has fallen the distance of h from rest? It's really not that much different from what we started out with, right? So we could start out with, again, total energy initial is equal to total energy final. There's only one force, there's only one energy, and that is the potential energy of gravitation for this mass, hanging mass. There's no kinetic energy for this, there's no kinetic energy for this, there's no kinetic energy for that initially, because it starts from rest. So I only have potential energy of small m initial that has to equal to, as this thing falls, this will gain kinetic energy. This disk will gain kinetic energy. And there's going to be the kinetic energy rotational for the sphere, spherical shell. Okay? So here, mgh is equal to 1/2 mv final squared, right, plus the disk is 1/2 I omega final squared, plus 1/2 I sphere, right, omega final sphere squared. So here, mgh is equal to 1/2 mvf squared plus 1/2. They want this left at I, right? Because this is a disk. However, this omega final can be replaced with v over r, right? So v squared over r squared, right? Plus 1/2 times, you have to look this up. The moment of inertia for sphere happens to be 2/3 mr squared. Replace that with v omega final as vf squared over r squared. So notice how this r will cancel out with this r squared, right? And this, I guess, 1/2, and this will cancel out. So mgh is equal to all this mess, right? So I have 1/2 mvf squared plus I omega, I'm sorry, I v f squared over 2r squared plus 1/3 mvf squared. So if you factor out the vf squared, we have 1/2 m plus I over 2r squared plus m over 3, right? Which is equal to mgh. So, I guess from here it's just the algebraic manipulations, right? So if you multiply everything by 2, right, and then divide everything by m, so if you multiply everything by 2, you're going to get 2 mgh is equal to vf squared times m plus I over r squared plus 2/3 m, right? And then if you divide everything by m, you get 2gh is equal to vf squared times 1 plus I over 2r, sorry, mr squared, right? Plus 2m over 3m, right? And then it just becomes vf is equal to square root of 2gh whole thing over this mess, right? 1 plus I over mr squared plus 2m over 3 small m. All right, that's the rest is the algebra. I'm going to stop there for today. I'll post the rest of the other 2 problems on Schoology. I don't think I have time to finish, but it's all pretty much the same thing. Okay. Just use parallel axis theorem for the last one. All right. Thank you for coming. And I'll stop the lecture here.